go. Now the mic's on. This is half the fun of pandemic broadcasting, is someone's mic should be muted at some point. Welcome in. Good morning, good afternoon, everybody. My name is Jesse, and I am your virtual adventure guide here with Exploring by the Seat of Your Pants. Now, I know we've got a lot of familiar faces in the crowd today, but if you are new to what we do, we are all about bringing conservation, adventure, and science into classrooms around the world. And our favorite thing to do is to go on virtual field trips, some of the coolest people and places, unique locations and facilities around the globe. And today is a special treat as we get the chance to go to the Canada-France-Hawaii Telescope. So I'm going to explain a little bit more about that in just a second, but I wanted to put a housekeeping note out there that we will be doing a Kahoot quiz today. So if you are live with us, if you are on YouTube and you're joining in the chat there, feel free to bring up this game pin, kahoot.it, and then 599-5190 as a separate tab. We'll be doing a little quiz between the talk and Q&A. So the Canada-France-Hawaii Telescope is this incredible multi-country international collaboration to probe the secrets of the universe. And it's set on Maunakea, one of the most beautiful, iconic places on this planet. I'm so excited to turn it over today to Daniel Devost. So he is the Director of Science Operations at the CFH Telescope, and he's going to be joining us today to walk us around, show us a little bit about what's going on there and some of the cool stuff they get up to, and so much more. So without further ado, I'm going to turn it over to Daniel to blow our minds over the next 20 minutes or so. Daniel, welcome into the broadcast, and nice to see you again, man.
Hi, Jesse. Nice to be here. Thank you for inviting me.
We have got classes from all over the continent today. You're at 8:30 in the morning. I'm in Newfoundland. It's 4 o'clock here, and we've got pretty much every time zone in between across the continent. So it's a very exciting broadcast. And if you want to dive in with your presentation, pull that up on your screen. We will be good to go.
Okay.
To learn a little more about what you guys are up to there. Awesome.
Okay, thank you. So I'm currently located in the remote observing room at the Canada-France-Hawaii Telescope. And actually, our remote observer here, Lisa Wells, is just finishing her shift. So it's the morning here, and Lisa was here all night to gather science data for us. So first, our location. So we're located in Hawaii, so right in the middle of the Pacific Ocean. So that's what makes, that's one of the things that make this site much better than any other site on Earth, except for a few ones maybe. But that's one of the best sites to do astronomy on the island, in the world. And here's the main islands of the Hawaii archipelago. And we are right here in Waimea. So it's a little town, a tiny town, located between Kona and Hilo. And you can see, Jesse, do you see my cursor? So we're located right here between Kona and Hilo. And
yes, we do see your cursor, by the way. Sorry, it gave me fits with the button there for a sec. But
okay, that's good. All right, perfect. So like I said, I'm right now in the remote observing room, and I will show you a little bit of what how things are working here. So Lisa is actually closing the vent doors, what we call the vent doors on the dome. And she's doing that completely remotely. We're about something like 50 kilometers away from the summit of Maunakea, and you can see that door closing right there. So we're controlling the whole thing remotely here. And you can see here all the things that Lisa used overnight to perform the observations. And you can see here, this is one of her one of the observations that she did last night, and it's the Taurus Helmet Nebula, I believe. Is that right, Lisa?
Yep.
Yeah. And this is
the helmet. You can see the horns coming off this way.
Yeah, that's right. Yeah. So these are raw images that have been taken with actually one of our instruments that has been built in Canada, actually, at Laval University, my home university, and it's called CETEL. So I won't talk to you too much about it today. I'll talk about another one of our instruments, but I'll get to that a little later. And here are all sorts of tools and diagnosis that you can see on her screen that she uses to perform the observations. And here there's another screen where it's the telescope control system, basically, where it tells Lisa where the telescope's pointing at, where it's, if we're guiding or not, and all sorts of things that she needs to do overnight. So, you know, the telescope keeps her really busy, and now she's moving the dome. So these are sounds, actually. I don't know if you heard that, but that was a sound from the summit, a microphone that we have installed here that tells people that the dome is moving. And if you go back here, I think you can see the dome slightly moving. Yeah, there you go. So she's turning it to park it for the day because she's done with her day. And thank you, Lisa.
Sure.
And here you have other screens and other things that are useful for our remote observers. So you have on this screen here, it's a weather map, basically, because we need to know if bad or good weather is coming. And here you have a graph of a quantity that we call seeing. So I will take a little bit of time, I'm sorry, to explain this. So this graph here is really the reason why people love, astronomers love Maunakea. This is because last night wasn't too good. You can see those points here cluster around about 1.2, which is not a good night for Maunakea. Maunakea usually will go down. I was hoping I could show you that, but unfortunately I can't. In this graph here, Maunakea usually gets you down to 0.4, 0.5, and this quantity that we're measuring is called, we call it seeing. So it's a measure of the scintillation of the stars, how they scintillate. We see that on our cameras, and we can actually measure it. So
very cool.
Back to the presentation, and please give a big thank to Lisa.
Yeah, I was going to say, like, we'll do a big shout out to Lisa for joining us after a whole night of no sleep doing telescope stuff. Thanks for being part of the program.
No problem.
Okay, so now that I've shown you how things work here, this is Waimea. This is actually where I am. I came in that way this morning, and where Lisa and I are right here on the side of the building. And now we're going to move to the summit of Maunakea. So like I told you earlier, the summit is about something like 50 kilometers away, 40, 50, maybe 60 kilometers away. And here's what it looks like. So at the summit of Maunakea, there's something like 13 telescopes that are doing astronomy. And we're doing it on a land that is sacred to the Hawaiians. And we're very grateful that the Hawaiians allow us to do astronomy, top-level astronomy at the summit of this mountain. Maunakea is 4,000 meters high, 3,900 and something. So it's pretty high. If you go up there, there are altitude effects. You can feel out of breath. So it's quite high, and that's why the height combined to the fact that you're surrounded by a body of water, a gigantic body of water, which is the Pacific Ocean, helps the atmospheric conditions above Maunakea and gives us some of the best conditions in the world. So here's the telescope. You saw it a little earlier in on Lisa's screens. So it's a 5-story building. So just to situate you guys here, this right here is a door. So that's the height of a person right there. So it's a gigantic building, and it's a big telescope and a big structure. So it's the telescope is on the 5th floor. So here's the scope here. So just to give you an idea of the scale, you have one here, one here. So these are 3 people that are chatting at the moment. We're chatting at the moment of taking the picture. So the CFHT the mirror is right there. So CFHT is a 3.6 mirror telescope. Even though I've been saying that everything is big, it's a big mirror, it's a big telescope, and it's a big building, 3.6 meters in this day and age is about mid-size, basically. So on the mountain, let me go back. You have these two here, which are the two Keck telescopes from the Keck Observatory, and these are two 10 meters telescope. 10-meter mirror, and you have here the Subaru telescope, who has an 8-meter mirror, and here Gemini, who has an 8-meter mirror too. Subaru has 8 meter. I say 10. It's 8 meters. So let's go back here. So what do we do with these? Oh yeah, just to give you an idea of the size of the mirror. So here are three of our very talented engineers that just completed what we call the aluminization of the mirror. So what that means is that we strip completely the aluminum coating on the mirror, we take it out, we clean it up, and we put a brand new one. And that's right after this whole process. This process lasts something like 2 days, 3 days. And basically, it's a long and complicated process, but it was successful. You can see the surface of the mirror here. That's very highly reflective. And we do this about every 3 years in normal conditions. We've been doing it lately a little more often than we'd like to, but it's a very involved operation. We need to dismantle the telescope completely. Bring the mirror on the 3rd floor, and that mirror weighs something like 14 tons. So it's a big mirror, and it helps us collect photons so more efficiently. So how we use the telescope is with instruments. So this is all something that everyone does in astronomy. You have a mirror, and then you put an instrument in front of the mirror, and you collect the data, you collect your photons. These instruments normally in optical astronomy are literally cameras. It's the same type of well, not the same type, but a camera as the ones you have in your cell phones. And here I've outlined the instrument that is on the telescope right now, which is called WIRCam. So WIRCam stands for Wide Field Infrared Camera. So this is a camera that we put on the telescope on a semi-regular basis. The instrument that I'm going to talk to you more about today is called Spirou. So this instrument is actually located, going back and forth, on the 3rd floor of the observatory, which is about at this level here. So what we do, we take a piece of fiber optic, really expensive fiber optic, and we run it all the way down, about 35 meters, all the way down to the 3rd floor where the spectrograph is. And this here is the 3rd floor of the observatory. And this whole thing here is the spectrograph. So Spirou is a high-resolution near-infrared spectropolarimeter that can, and velocimeter that can characterize planets around stars. So it's a planet hunter. And you can see here this vessel, this big vessel. It's about 6 foot high. So it's a big vessel. It's a big instrument. And this whole thing here, is the instrument itself, which you can have a better view of here. So you can see here, that's the vessel, this whole thing. So this vessel comes inside and over the instrument. So when the whole thing, this vessel comes in, and when the whole thing is closed, all you see is that vessel. And you can see here these big lenses and all sorts of optical component that make up Spirou, which is our latest instrument. It's our most modern instrument, and it's like I said, used to hunt for planets. So how things are going fairly well in the planet hunting world these days in astronomy. But before I get there, I just want to explain to you what a spectrograph is. So you have here a cartoonish depiction of a spectrograph. So basically, a spectrograph can be thought of as a prism, like I have it here, or it can be thought of as a rainbow. The water droplets that produce the rainbow are actually a spectrograph that display the spectrum of the sun. So what happens with these components, like here with the prism splits the color of light into its different components. So you have it here from red to blue, and then we use a good old camera. So here I use a camera from another instrument, but it's just to show you. So here, this is a CCD camera, same type again of cameras that you have in your phones, but much bigger, and it collects the photons. So we collect the spectrum with we basically collect the color, the different colors of the stars, of the rainbows of these stars, not only the star, the sun, like our the rainbows that we know and love. So here's how SPIRU works. So like I said, the SPIRU is a planet hunter. So it will help us characterize planets, and it uses the radial velocity technique. So I have it here on this cartoon. So what you see is when a planet revolves around the star, which is on the left-hand side, it makes that star wobble. And this is just the properties of stars and planet. The sun also wobbles around the center that's inside the sun. So there's a wobbling to the sun, and that's due to all the planets that are around the sun. So all the systems, all the stellar systems in the universe basically behave like that. You can see a wobble in a star, and that tells you that when you see a star wobbling like that, it tells you that there's something around it that is going around, and what you want to have is an instrument that will help you characterize that wobble. And SPIRU is exactly that. So you can see here at the bottom, on the right-hand side where my cursor is, it's a spectrum, basically. And you see these two black lines. It's just to outline absorption lines in the spectrum. So in a spectrum, you can have, black lines, basically, that are absorption caused by elements. I won't go too much into the details on that. But the wobbling makes these lines move on the spectrum. And this is really typical of how we detect a planet around a star using the radial velocity technique. So SPIRU is unique in a sense that it's extremely sensitive to the movement of these lines. So it's sensitive to it basically at 1 meter per second. So if you can imagine 1 meter per second, you have a meter is about that long, and you pass that distance in 1 second. So we're able to measure the speed on stars that are, millions of miles away, millions of that are light years away. So it's a very unique instrument, and it's difficult to do. That's why this instrument is so complicated, because measuring radial velocity at this precision, at this level of precision, is very difficult. And SPIRU does it really well. It's one of the best instruments in the world to be able to see those lines. And once you have those lines, you can characterize the planet. You can even discover new planets. So SPIRU has discovered some new planets around stars. And basically, you get this here. So this is the exoplanets, NASA exoplanets database, which is it's on the internet. So all you need to do is type NASA exoplanet database, and you will see that right now there are 5,190 confirmed exoplanets. So what does that mean, confirmed? Is that all the techniques that we're using to these planets have some caveats or need to be confirmed, or you have a detection and then you use a different technique to see if it works, and all of that together, then at some point you're sure it's a planet, because there's many things that can induce an effect that's similar to the wobbling or other effects with other techniques that are used to detect planets. So what we're finding is quite interesting. There's the highest number of planets with the 1,800 is Neptune-like. So they're Neptune-like planets, cold planets that are gas giants. And the gas giants is actually the second one. It's a little subtlety in the classification here that I won't go through. And there's also super Earths. So super Earths are planets that are bigger than the Earth. And we do see those when we characterize the planet. So that's what I'm talking about when I say characterizing a planet, is that you want to know what it is, what it looks like, what is it made of? Is it a gas giant that's made up of gas? Is it Neptune-like? Is it a rock? Because with the Earth, Mars and Venus and Mercury, these are rocky planets. They're basically a rock. So we can determine that also. And there's those 5 here, which I haven't looked into much further, but they're unknown. So we're not able to classify them with what we know. So these are really interesting things. So here's the different the different methods of detecting and classifying planets. So you can find all that on the website. So here you have the transits, which are used by 75% of the time of the planet detection. So transit is when a planet, like you see here, passes in front of its star and the light from the star dims. So I don't know if, I don't think many of you saw Venus pass in front of the sun, but there's plenty of images on that on the internet. But in 2012, I think, if my memory serves, Venus passed in front of the sun, and you could see on the sun a dark spot like that. Of course, you look at the sun with, proper equipment, and you look at it with a telescope with a sun filter in it, not to hurt your eyes, and you could see a black dot that's right in front of the sun. So that happens also with other stars. However, the alignment of the planet with the star has to be just right for us to see. But this is a very popular technique that finds a lot of planets. So you can find them because the luminosity of the planet, the luminosity of the star diminishes as the planet passes. And about 20% of the detected planets come from the radial velocity technique, which is what we are using at CFHT with Spirou. And then 2.6% comes from microlensing, something I won't go through. The other one is imaging, so 1.2%. So now telescopes, and we don't do that here at CFHT, but in other places with bigger mirrors and more sensitive instruments, they were able to actually take a picture of the planet. And the picture of the picture of the planet is not. It's just a point of light, right? You see on the internet everywhere images of planets, and these are artist conception based on what we can infer from characterizing the planet. We can have an idea of its color. We can have an idea if it has clouds in its atmosphere and things like that. And you give that to an artist and he makes up a nice whole planet. But just so you guys know, we cannot take full-blown pictures of planets right now. But what we can do is take a picture and see the dot of light that's a planet. And that in itself is extremely difficult to do. And it's just something that has come around in the last 10 years or so when people started doing real imaging of planets. So I think I'm going to stop here. Just so you guys know, we also have collaborations with scientists, like Jesse was saying, all over the world, and also in Canada. So one of them is Frédéric Baron, who's going to give the Exploring by the Seat of Your Pants talk next week. And that's actually a picture of her taken on the catwalk at CFHT. So she came here when she was a student. We worked with her, and she worked, of course, on Spirou, trying to understand the data, trying to analyze it, get better things out of the data that we give her. And she's part of the Institute for Research on Exoplanets, IREX, which is at the University of Montreal. And she's going to tell you guys way more than I can ever do about exoplanets next semester. So I will stop here, Jesse, and take questions.
Perfect. Well, thank you so much, Daniel. While you're coming out of screen share, I'll note that we're going to do our little Kahoot quiz together. A lot of you are already queued up there, which is fantastic. So feel free to type in kahoot.it and bring in that game pin. And yes, Frederica joined us in French on the 27th. She joins us in English regularly throughout the year as well. We love exoplanets as a topic here at Exploring by the Seat of Your Pants. So hopefully, no matter what, you guys get those opportunities to learn more about incredible exoplanets. I'll make sure you have that NASA link as well for the end of the broadcast to make sure you can keep the learning going. But for now, Daniel, we're going to dive in with our Kahoot. 4 quick questions, folks. For those who don't know about Kahoot, the faster you answer, the more points you get. And you don't win anything, but you do win Daniel and I's everlasting respect if you happen to end up on the podium today. So that's worth something, I think. All right, our first question coming up. Here we go. Which island is the Canada-France-Hawaii telescope located on? This is part of the early part of the talk before we got to go hang out with Lisa for a while there. Is it Oahu, that place with Honolulu? Is it Maui, Kauai, or is it the Big Island? 8 more seconds. A lot of you are having trouble with this one. I know there's a lot of you. And get those answers in 4 more seconds. Oh, well, I'll tell you this. It's the island that I've been to because I went up to see the telescope, and this is a really low answer. Only 8 of you got this right. It is the Big Island. So it's the one with Kona, Hilo, Volcanoes National Park, all the manta rays off the coast. It's a very, very special part of the world. But Purple Sphinx has our lead right now. Okay, Daniel, we're going to go to question 2. This is a true or false one. 3 more questions to go, and then you guys can ask Daniel all your questions. Telescopes can see back in time. True or false? Well, that sounds ridiculous. Surely telescopes can't see back in time, can they? What do we think? Dan, you want to give us a hint?
Should I answer?
We got 4 more seconds. Oh, everyone got it in. Most people thought this was false, but it's true. Telescopes.
It is true, indeed. And just to give you guys a local example, the light from the sun, it is due to the fact that the speed of light is finite. So the light that comes from the sun is actually takes 8 minutes to come to Earth. So the sun that you see with your eyes is 8 minutes old. So you see back in time, basically. So, and the farther you go, the longer this time base becomes. And if you look at farther away galaxies, then they're millions of light years back in time.
Crazy. I mean, that fact, truly, I want to say, like, I live for science. I live for exploration. I've been interested in this stuff since I was 4 years old. That fact never ceases to not bring, like, a huge smile to my face. It's just ridiculous that you can look back at a galaxy 1 billion light years away, and that means you're not seeing it now. You're seeing it as it was 1 billion years ago. That whole, everything could be gone for all we know. And it's just, anyway, mind-blowing. So telescopes are time machines, folks. Let's see how that affects our leaderboard. Noble Griffin takes our lead. Happy Newton second. Let's go to our third question. Okay. WIRCAM, WIRCAM, our telescope that Daniel talked about earlier in the broadcast, sees in what kind of light? Gamma rays? Does it see what turns the Hulk into the Hulk? Ultraviolet? Visible light, so what we see with our eyes? Or infrared? This is a very
in the name of the instrument.
Yeah, it might. One of those things has an eye in it, maybe. There's your hint with 0 seconds. Most of you got this right. Infrared is your answer. Way to go, guys. All right. A few of you thought ultraviolet. Good guess. Another not visible thing. Rockstar Boa takes our lead with one more question, and then I'm looking forward to your questions. All right. The Canada, France, Hawaii telescopes help us detect potentially dangerous asteroids. We've got this screaming T-Rex picture here, which all art about the end of the dinosaurs has T-Rexes screaming in it. So we talked about planet hunting today. We talked about other things. Do we think that this array, this group of telescopes, is involved in the hunt for potentially dangerous asteroids? And our answer is, most of you got this right. True. So NASA, the European Space Agency, the Canadian Space Agency, all have programs to help detect potentially harmful objects that are heading towards the Earth. So great job, guys. Speedy Bear is our third place winner. These new dancing animals is a new part of this. This is very exciting. And number one, our winner today, let us know who you are in the chat. Rockstar Boa, way to go. All right, Daniel, we're going to head to Q&A. So
Okay.
Ms. Solomon's class, I know your devices are off, so you guys can share in the chat with us here in StreamYard. Mr. Barron's class joining us in Manitoba today. If you guys want to kick us off with a first question, you are in the broadcast, and we can hear you guys. Hey, guys.
Hey, we got a hand asking a question right here.
Perfect.
Ask your question.
Can you see Mars through the big telescope?
Can you see Mars? I bet. What do we think?
Yes, that's right. We could see Mars. We could observe Mars if we wanted to on our telescopes. However, we don't do that very often because it's very bright and it's really close. And you can do it with a smaller telescope or a telescope in space. So we don't observe Mars often, but I don't remember having observing it since I'm here.
Wow.
But
We've done the moons.
We've done the moon. Yeah, that's right. We've done the moon once. Yeah.
And by the way, I want to note for our classes that the moons of Mars are really freaky and weird because they're kind of like potatoes. Phobos and Deimos are really strange moons. But I love this, the idea that it's so close and so bright that we want to be looking at things that are further afield. We have other instruments, other missions that help assess Mars. It's one of the most studied places in the universe outside of the Earth. But great question to kick us off, guys. All right, Austin International, grade 4s. If you guys want to unmute your mic and come on in, you're good to go. Hey, guys. No, you're good. Perfect. Just unmute. Hi, everybody. Hi, everybody.
Hi.
Hi, hello.
Hi.
Hi.
Ok, alors, qui veut poser une question? Benoît, vas-y.
So we went to the Fort Davis McDonald Observatory, and I was wondering why is Hawaii like a better place to put the observatory?
Yeah.
It's a very good question. Thank you for asking it. So, Hawaii is in the middle of the ocean. So the ocean has a cooling effect on the atmosphere, and on top of that, Maunakea is really high up. So there's less air between the space and the telescope, and that produces air turbulence. And basically that mingles the light, that makes the stars twinkle. And that, for telescopes, that is not good. This is not something we want. We want that twinkling to be as small as possible. So the fact that Hawaii is surrounded by the Pacific Ocean, it's in the middle of an ocean that cools off the atmosphere, so that lowers the turbulence, and also the fact that the telescope is all the way up at 4,000 meters, that minimizes the amount of air between the telescope and space, and minimizes also atmospheric turbulence. So that's why Maunakea is loved by astronomers.
Now, I want to stress for our students, if you get the chance to visit an observatory, wherever that may be around the globe, it is an opportunity you absolutely should not pass up. One of my very favorite experiences in my life was seeing Saturn's rings through a telescope, something that I'd seen in pictures thousands of times. And in Toronto, in the heart of a major city with lots of light, lots of pollution and all that stuff, seeing that was a really special experience. But it does speak to the fact that the Canada, France, Hawaii telescope is really beautifully positioned to get some really fantastic data. So great question, Austin International. Let's head to Abaca West, our 4B crew in Glenview, Illinois. You guys want to come on in? You're good to go. Hey.
Hi. So my question is, well, in class we learned about like protesters of Native Hawaiians. How is it like living with that, and like how does that affect?
You mean the conflict with the natives?
Yeah, so that I mean, the end of France, or that region sort of made the news with the fact that people were protesting the building of additional telescopes there. You began your talk talking about the Hawaiians allowing you to build these things there, but if you could speak to that, that'd be fantastic.
Yeah. So this is something that's been going on for a while, and it makes all astronomers really sad, to be honest. Nobody wants to have this kind of conflict, and certainly not, make a native population mad at the fact that we're using the telescope on top of their sacred mountain. So for the Hawaiians, the mountain is sacred, and they perform religious ceremonies up there, and they go there for all sorts of things. And they don't like the telescopes being there, and we try to be respectful, accommodate them more, and try to also give them access to high-level education, because telescopes are really high-level science, and we have high-level science positions, and we can also help them with education. So we try, to make to
Make
be
the best
respectful of what they do, and it's a difficult problem, and no astronomer want to see people arrested for blocking for astronomy or blocking the road and things like that, because these are things that happen, and nobody likes that. It's something for myself that I find hard to do.
It's been interesting seeing, even over the course of the 7 years that we've been running broadcasts, how much science has changed in the ways that they go about involving community members in the decision-making when it comes to building facilities like this. So again, if it were to have started today, if there was nothing on Maunakea, there would have been probably a lot more decision-making and partnership and collaboration and discussion when it went into the building of that facility to begin with. It's been in place for many decades now, and so you run into these issues down the road that have changed how people perceive these facilities, and I think it's a really great question. So kudos to you guys for doing research in Ms. Michael's class, and I really appreciate the question. We're going to head to our Vancouver, BC class, Ms. Meyer's group, St. Mary's School in grade 6, and then we'll head to Ms. Becker's after that. Time flies when you're having fun. We're nearing the end of our broadcast, but St. Mary's, Vancouver, come on in. Hey.
Oh, go ahead. There you go.
Hello. My question is, how long did it take to install the telescope?
To build it?
Yeah.
Well, the CFHT, it took 10 years to get it together, have the plans and everything, then took 10 years to build it. So these telescopes, and that's a good working around number. These giant telescopes, keep in mind that you got to bring all the hardware all the way up at 4,000 meters on a road. That's not necessarily, that's not a highway, that's for sure. And it takes about 10 years to build all of those up. The last one that was built up there was Gemini, and took about that 10 years.
Even for space telescopes, it always seems to be about the decade mark. And so it's always, I like highlighting the fact that all things considered, the cost about these amazing tools, these amazing ways of so low, but do take a lot of so much effort planning them. So great question. All right, Mr. You guys want to you're good to go. Come on in.
Hi.
Unmute this.
My question is, how wide is the container where the telescope is?
Can you repeat it? I missed the first part.
My question is, how wide is the container where the telescope is in?
Jesse,
The big building, how wide is the container that the telescope is in? Like, how wide is the building, I suppose?
oh, you mean the scope itself?
Yeah.
So it's 4 meter. The telescope is the mirror is 3.6 meters, which is pretty big, and the container around it is a little bigger, but not a lot bigger. I would say about 4 meters wide to hold the telescope. Yeah, to hold the mirror in place.
Daniel, I know we could talk all day about the telescope, but I want to make sure our audience can get to next periods if they have to. So I want to share some resources to keep learning going. If you guys want to learn more about the Canada, France, Hawaii telescope, they've got a beautiful education page at the link below. So cfht.hawaii.edu. And then Daniel shared this amazing exoplanets resource earlier in the broadcast. So exoplanets.nasa.gov. NASA really is the gold standard for amazing educational resources. So if you want to learn more about the hunt for other planets throughout the universe, do check out that link. And of course, if you want to check out Frederique's program, or if you have teacher colleagues that happen to be bilingual or French, send them to her program on the 27th. We'll also be having her in English in the months to come. Daniel, is there a last message you want to leave with all our kids from all around the world today about your telescope and the work that you do there?
Sure, yeah. So one thing that people think is that if you want to work on telescopes and big astronomy like we're doing here, you got to be an astronomer, right? And that's not necessarily true. I mean, here at CFHT, we have 8 PhD astronomers, and we have 4 remote observers. But the remainder of the company, which is 45 people, are engineers, mechanical engineers, electronics engineer, software engineers. So, studying astronomy is not necessarily the only way into doing astronomy. But the one thing you got to do, though, is that if you want to work in astronomy, you got to stay in school and get a college degree. That helps a lot.
Fantastic. Daniel, it's so nice seeing you again, man. It's been such a pleasure. But how we end every broadcast, I'm going to bring in all our kids to be as excited as I am and say a big thank you and farewell. So Austin International, Avica West, St. Mary's, and Miss Becker's class, unmute your mics. Join me. Thank you so much, everybody. And have a good day.